Hello and welcome to the Plus podcast. My name is Marianne Freiberger. At this time of year in England, we are all very likely to check our weather apps on our phones to see if we stay dry when we leave the house. Now, typically what you see on a weather app are percentage chances. So the app might tell you that there's a 60% chance of rain or a 10% chance of snow, for example. These percentages aren't the result of guesswork. They are there because the people who run the computer models that produce the forecasts have run the model not just once, but a whole bunch of times, each time with slightly different starting conditions, to produce a whole bunch of forecasts. And if in 60% of this bunch of forecasts it's predicted to rain, then that's the 60% that the weather app gives you. Now, this technique is known as ensemble forecasting, and as we'll find out in this podcast, there's a good reason for why it's necessary. At a recent event organized by the Newton Gateway to Mathematics in Cambridge, we were very lucky to meet the person who pioneered ensemble forecasting. His name is Tim Palmer. He's a Royal Society research professor in climate physics at the University of Oxford, and he's a leading expert in climate science. In this podcast, Tim tells us about his pretty groundbreaking idea of ensemble forecasting, but he also tells us about what the uncertain business of weather and climate forecasting has taught him about uncertainty in general as it crops up in many other areas of life and the world. This is something that he explores in his new book called The Primacy of Doubt. He also tells us why he thinks it's high time we had something equivalent to CERN for climate modeling. CERN, of course, being the multinational, highly sophisticated and very expensive research center dedicated to fundamental physics. But before we find out what Tim means by his call for a CERN for the climate change, let's go back to ensemble forecasting. We started off by asking him why it was necessary for him to come up with the idea in the first place.
Well, yeah. So, I mean, when we make predictions in general terms, I mean, everybody knows this. Predictions are uncertain. It's quite difficult to forecast the future with any degree of certainty. But the interesting thing is that, this is typically true of all systems that we predict, whether it's the economy, the weather, pandemics, and so on. We're dealing with mathematically what would be called nonlinear systems. And the interesting property of nonlinear systems is that the growth of uncertainty in a forecast is not the same for every forecast. So there are certain conditions, if you like, or certain situations where we can actually make forecasts, we can in principle at least make forecasts with quite a lot of confidence, because we know that during those periods the system is relatively sort of stable, which means that small uncertainties don't grow especially rapidly. Conversely, there are other occasions where uncertainties can kind of grow explosively and destroy any sort of very specific prediction, almost from the start. The question is, can we determine ahead of time, before we make the prediction or at the time we make the prediction, can we tell whether we are in a predictable state, or the system that we're studying is in a predictable state, or whether it's in a very unpredictable state? And that's where this ensemble prediction idea comes from. Instead of just running a single forecast, we would run multiple forecasts varying, what we consider to be the most important uncertain, parts of the initial conditions or uncertain parameters in the models or that sort of thing. And, just look and see, do all the ensemble members agree with each other? Do they all start diverging rapidly away from one another? So this gives you a kind of heads up, if you like, before you even begin, whether this is going to be a kind of a reliable forecast or a very kind of uncertain forecast, let's say. And there's all sorts of implications about, how we then make decisions based on those forecasts that arise from that.
Mhm. So if we're thinking of a concrete example, like the weather, for example,
Yeah.
in very simple terms, so is it the case that you would, so you start off with some initial conditions about current temperature, pressure, wind, or whatever might go into the model that forecasts the weather. Do you then run the model for a set of different initial conditions, so you get an ensemble of forecasts?
Yes, that's right. We would, when you take, when you make measurements of the weather, it can either be with, thermometers and barometers and things, although these days, most of the measurements are made from space-based satellites. But in any case, no matter what type of measurement you're talking about, there's always a little bit of uncertainty in that measurement. There's also the problem that the model itself is always a kind of a finite representation of the atmosphere. The atmosphere is a very, very complex system, and that creates uncertainties as well. So what you do is you create an ensemble of initial conditions, each of which is consistent with the observations, but they all differ very slightly from one another. And then I should say also, when you run the model itself, although the underlying equations from a say strictly mathematical point of view are what we would call deterministic equations, there's no uncertainty in the underlying equations. But when you try to code these equations in a form that a computer can understand and sort of and try to solve, then inevitably that process of making them, computational introduces uncertainties. And so a second source of uncertainty, in addition to the observational uncertainties, are actually the uncertainties in the computational representation of the underlying equations. And again, these are all fairly small. I mean, it's not like these are mega big uncertainties, but in a chaotic system, which is basically what we're dealing with, these small uncertainty, this is a sort of the butterfly effect, that flaps of butterflies' wings can have big effects. And so these small initial uncertainties and small model equation uncertainties grow with time, and eventually they become large. But the point about ensemble forecasting is that the time at which these uncertainties become large varies from one starting condition to another, and that's a consequence of the non-linearity of the equations. And so the ensemble kind of tells you how far ahead you can go before the uncertainty completely sort of swamps what you can do.
And that's because you check how close the different members of the ensemble of forecasts are. Is that how you do it? You look how close they remain, and as long they're close.
Well, a very, I mean, yeah, I mean, although what many of us are used to these days, which is a kind of practical tool, if you like, is you just calculate from the ensemble the number. For example, if you wanted to know if it's going to rain in Cambridge the day after tomorrow, you would count the number of ensemble members where it's raining, so typically an ensemble might have 50 members. And if in, let's say, 10 of the 50 members, it's raining. So then a simple way of representing that is to say that there is a, 10 out of 50 or 20%, 20 out of 100 or 20% chance of rain. And that's what you see on your weather app. When you look at a weather app and it says 20% chance of rain, what it means is in the ensemble that they've run, in like 10 out of 50 or 20 out of 100 ensemble members, it's raining. That's what it means. So that's a kind of a simple way of giving you a very kind of simple heads up on the confidence, if you like, you can have in that prediction.
Mm-hmm. And you already mentioned that this kind of technique can be used in other contexts. And you've also just written a book which talks about uncertainties in all kinds of areas and what we have learned from weather and climate. Could you tell us a bit more about that?
Yeah, I mean, the book's called The Primacy of Doubt. And the phrase comes from a biography by James Gleick of the great theoretical physicist Richard Feynman. And Gleick says about Feynman that he believed in the primacy of doubt not as a blemish on our ability to know, but as the essence of knowing. And that really does resonate very strongly with my own kind of philosophy that, we often perhaps think of doing, risk analyses and uncertainty analyses as a kind of afterthought. But the truth of the matter is that we should be treating uncertainty as important a variable as anything else, and sort of integrated into our thinking. And my, strong belief is that from a theoretical point of view, we can actually understand the way the world works. And I have several chapters in the book about this, for example, in relation to quantum physics. I think we can understand better the way the world works by trying to really dig down deeply into understanding why systems are uncertain and what that kind of means at a deep level. But at a practical level, the ensemble technique, one area where it's certainly been used a lot is in COVID prediction. A number of different epidemiological groups have developed COVID prediction models, and we now have as COVID developed, people realized that the best way to offer advice to policymakers, to governments around the world about what type of policy to implement, i.e., do we want to restrict people's interaction, or do we want to just kind of carry on and hope everything will be fine, was best informed by not just taking one of the models, but by kind of pooling together all the information from all the models into what I would call a multi-model ensemble, which is, by the way, a technique which is typically used in the IPCC climate change assessment reports. They're based on multi-model ensembles from different groups around the world. And of course, the importance of an ensemble is that it not only tells you, if you like, the most likely outcome, for example, of number of hospitalizations or deaths or whatever, but it gives you a sort of what you might say is a reasonable worst case scenario for what might happen. And of course, that is important for policy. It's not just about the most likely prediction. It's kind of what could really, in a worst case, happen. And I think that clearly did influence, for example, here in the UK, I think that really did influence our policy. The idea that, the NHS would run out of beds and, people would be sort of left on the streets almost, was too awful to contemplate. So a lot of the policy on COVID was predicated on ensuring that worst case scenario didn't happen. And yeah, ensembles are kind of vital to be able to quantify that type of worst case scenario. So that's one place where things have become well developed. In the book, I sort of discuss things like economic prediction and actually also conflict prediction, trying to to predict the trouble spots in the world.
Yeah, and everything seems to be happening right now. Economic problems,
that's
pandemic,
right.
And climate change, of course. And thinking about climate change, so there are, just as there are weather models, there are climate models. And you've called for a CERN for climate modeling or climate change. Can you just say what you mean by that and why?
Well, yes. We there's no doubt that the climate is, our global temperatures are warming, the climate's changing, the temperatures are increasing, and that's due to our emissions of carbon dioxide. So that's kind of without any kind of doubt at all these days. But increasingly people want to know more than just that. They want to know what actually will be the climate of their region, in the coming, say, 50 years. And you could think of two types of weather which are both consistent with global warming. One would be kind of hotter, more heat waves, more drought. But conversely, you could imagine another region being dominated by stormy, weather which produces flooding, the sort of thing we saw in Pakistan, for example, this summer. And a country that is looking to adapt, to make its society more resilient to climate change, so adapt to climate change. I mean, these are kind of order one questions. Is the climate of my country going to be, hotter and drier or wetter and stormier? It's kind of, hard to imagine a more basic order one question. The problem is, if you look at the ensemble, this multi-model ensemble of current generation climate models, you find, and you can see this if you look at IPCC reports, you'll see, this is very clearly illustrated, that the models just don't agree. We can't really be sure, even of the sign, whether the precipitation, rainfall, if you like, is getting more or less. So this is a kind of unsatisfactory state of affairs, and we can kind of pin it down to the fact that the models are pretty low resolution, certainly compared to weather forecast models. I mean, you mentioned weather forecast models and climate models. Probably the biggest difference between a weather forecast model and a climate model is that a weather forecast model is run with a grid of a few kilometers, whereas a climate model may have a grid of 100 or more kilometers.
The grid is basically the resolution at which you depict the Earth and its atmosphere and the oceans.
Yes, that's right. I mean, the underlying equations, like the Navier-Stokes equations, which govern fluid motion, so the atmosphere and the oceans, are, they describe every little whirl and eddy down to kind of infinitesimally small scales, and that's the nature of turbulence. You have these cascade of scales which goes down to small scale. So in the atmosphere, you have big cyclonic low pressure systems, but embedded in that are clouds, and embedded in the clouds are subcloud turbulence. But a climate model can't resolve all of that detail, and anything that gets less than 100 kilometers has to be represented in a rather kind of semi-crude, semi-empirical way with a simple formula, which everyone knows is not inaccurate, but you have a computer and that's the best you can do. So I, myself and a number of colleagues have been arguing that this is a kind of problem that, we know the Navier stuff. It's not like we don't know the physics. We know the physics at play. It's just we can't solve the equations with the level of accuracy that we would like. So our proposal is to create an international center, which would be an institute with multinational funding, which would enable the really top of the range supercomputers. So nowadays we're in what's called exascale, 10 to the power 18 calculations per second. But one of these would be dedicated to climate change, 100% dedicated to climate change. It's not something that, even a rich country like the United States is doing or is able to do. But, with a consortium of countries, for sure, we can do that. And calling it a CERN for climate change is really just making the point that, again, the Large Hadron Collider, which found the Higgs boson, was not affordable by any country, including the US. The US cancelled its own, high energy collider because it said it couldn't afford it. So, that's a great example of what can be achieved if we pool resources, pool human and financial resources internationally. And I think that climate change is such a kind of a pressing problem, an urgent problem these days. We need to kind of go beyond just saying that the Earth is warming. We need to be much more clear about it, what it means at the regional scale, because this is going to affect all sorts of decisions on, as I say, on infrastructure, on agriculture, on health, on the built environment, on disease. Everything is critically dependent on what climate change means at the regional level. And at the moment, we're kind of looking at the world through a very blurred glass with our coarse resolution models and so on. So that's what we're calling for. And I hope.
Well, it's astonishing it doesn't already exist, really.
Exactly. You might think it's a kind of a no-brainer, and actually, in terms of cost, it's not actually that expensive. It's kind of comparable with a satellite mission or something like that, which is not. We can afford those. So I'm hopeful. It'll happen, but it's like all these things. Science and politics don't often mix as well as you would like, and there are political issues.
And that's it for this edition of the Plus podcast. Tim Palmer's book, The Primacy of Doubt, is published by Oxford University Press. And you can find out more about weather and climate modeling on Plus by going to plus.maths.org and searching for weather or climate. Thanks for listening, and bye-bye.